So we're moving on to a unit called dynamics. If you want me to be fussy, kinematics, displacement, velocity, time, etc., that's the study of how things move. We're going to look at dynamics, or forces. And this is the study of why things move or don't move. Subtle difference. What's a force? A physicist would say that a force is a quantum interaction between two objects when they exchange force particles called There's everything that I'm going to be teaching you in this unit is technically wrong, because you can always dive down to a fundamental quantum level, and we're not going to do that. So I'm going to instead give you, although it's technically a wrong definition, a useful Physics 11, Physics 12 definition. A force is a push or a pull. Is force a vector or a scalar? Does direction matter when we're talking about which way you push or pull something? Oh, heck yeah. Force is a vector. So we're going to just have to pay attention to our directions when we're setting up questions. Symbol for force is capital F. And the units force is measured in newtons. Symbol or abbrev for newtons is capital N. This gives us a bit of a problem because N for directions is also north. But in context, if it's right after a number, you know it's newtons. If it's after an at symbol or in square brackets, it's a direction. And we're not going to be being that fussy this year anyways. We're often going to be interested in something that we call the net force. What I really mean by that is if you add up all the forces on an object and replace them with one uber force that takes all of them into account, that's the net force. And I'm going to throw you to the wolves right away by seeing if you can just kind of use your common sense. Let's suppose we're pushing on this object with 5 newtons to the right and 2 newtons to the right, and we want to replace that with one force. What's the net equivalent of that? Direction? 7 newtons right. Or east, if you wanted to put a compass on there. What if instead of 5 and 2 to the right, what if it was 5 to the right and 2 to the left? What's my net force? 3. And what you really did is you said, I'll let 5 be positive and 2 be negative, and I'm going 5 plus negative 2. That's not what you really did. You just went, well, it's 5 minus 2. But what you implied or you intuitively did is you said, there's got to be a directional component here. 3 newtons direction. What you'll often hear me ask is, which direction is the winning direction? In this case, right. And what we're going to decide from now on in this unit is we'll let the winning direction be positive, because that's just going to make the math way easier. Even if the winning direction is down, we'll let that be positive. Or if the winning direction is left, we'll let that be positive. Ooh, what's the net force here? This situation, if you know the net force is 0 newtons, hugely useful, hugely important. You can make a bunch of statements. If you know the net force is 0, you can say, I know certain laws of the universe apply. Physics 12, we redo Physics 11 in the first third of the course, but we do it in 2 dimensions, where we have things moving left, right, and up, down. And you learn what's called vectorial math. For those of you who are wondering, how would I add 6 right and 3 up? I would draw them tip to tail, 6 right and 3 up, and that right there is the net force. I would use Pythagoras and trig to find the the magnitude and the direction. Vectorial math. But we won't do that this year. I need to go on my Sir Isaac Newton rant. So put your pencils down. So here's what Isaac Newton said. Aristotle, garbage. He said, I can explain why the ball comes to a stop. I can explain why things fall. If all the forces are balanced, or the fancy phrase, the net force equals exactly what number? Yes. An object will either stay at rest if it was at rest, or keep going in a straight line at a constant speed. Fancy phrase, A is 0. If the net force is 0, there's no acceleration. You cannot be accelerating. Now remember, there's two ways that can occur. If you are stopped, you'll stay stopped. Or if you were moving, you're going to keep moving in the straight line at a steady speed, because that's not accelerating either. That explains outer space. In outer space, when you're away from gravity, the reason objects keep going in a straight line is because there's no force acting on them, and that's why asteroids and things just keep on going until they get under the influence of a star's gravity. Well, now the net force is no longer 0. Now they'll change direction and speed up or slow down. So you got to give credit. In 1680, he's already thinking, trying to explain outer space. It also works in reverse. If you know that an object is accelerating, which means changing its speed or changing its direction, or both, there must be an unbalanced net force acting on the object. The net force cannot be 0. We're going to use this often to figure out if we're missing a force. It's accelerating, and right now in my picture, all the forces cancel out. I'm missing a force. Or it's not accelerating, and right now in my picture, my forces don't cancel out. I must be missing a force. Newton's first, really, really handy. This explains why you feel like you're getting pushed towards the center, pushed towards the outside when you're in a car that goes around a corner. If you're sitting on a slippery seat, you want to keep going in a straight line at a steady speed. That's the law of inertia. The car moves sideways, and you're actually running into the door. Now, you think that that's because you're pushing against the door. It's actually because the car is having to push on you to change your direction. There has to be an unbalanced force applied to you. Pardon me? Yep. Okay. So imagine you're a passenger in a car and the driver makes a sudden left turn. What sensation do you feel during the left turn? You feel, this is also why your body is a backwards accelerometer. You're actually feeling the water, the liquids inside your body sloshing. So when I told you feel acceleration backwards, it's because what you're feeling is the liquid wanting to keep going in a straight line at a steady speed. Or if you're at rest, wanting to remain at rest. So contrary to what your common sense might tell you, you're not being pushed to the right at all. The driver steers the car to the left. You try and keep going in a straight line at a steady speed, and you're actually running into the door, and the door is pushing on you to get you to change direction. Your grandfather knew this. You talk to your grandpa, he might admit to this. Back in the 1950s and 60s, nobody wore seatbelts because they weren't the law, and most front seats were bench seats. So if you were a young high school kid or college kid and you were going out on a date, you would take some surfboard wax and you would wax down the front seat on the passenger side. And then you would drive with your hand like this and you would make a quick right turn and the girl would come sliding into your arm. Oh, hi, honey, that's really nice. And you would keep driving. Ask your grandfather. He might know of that trick. Okay? Well, and again, it wasn't that the girl moved into the guy. She kept going in a straight line. The car and the guy moved underneath into the girl, right? This is why I said you've got to rethink everything. So, as a general law or rule, next page. Next page. Any object tends to continue moving with whatever speed and direction it presently has. You may have heard Newton's first law phrased as objects at rest tend to remain at rest. Objects in motion tend to remain in motion, which to me is confusing. If you're accelerating, there's an unbalanced force. If you're not accelerating, the forces are balanced, which means the net force is 0. That's Newton's first. This tendency that objects with mass have to resist changes to their states of motion is given a special name. We call it inertia. The more inertia an object has, the harder it is to get it to change its motion state. Every object in the universe has this property that we call inertia. You can sort of think of inertia as the measure of the stubbornness of an object or its resistance to change. The more inertia, as an example, Earth has a lot of inertia. So when I jump and land on the Earth, I don't change its motion state very much. A ping pong ball doesn't have much inertia at all. And so I'm able to easily change its motion state by applying just a very small force. What has more inertia, a bicycle or a logging truck? Be obvious. Because the logging truck has more inertia, the logging truck is more difficult to get moving, more difficult to stop, and more difficult to turn around a corner. Because all of those require an unbalanced force, and it's got so much inertia, it needs a big unbalanced force. How do we measure inertia? Here is something that's technically wrong, but that will be accurate as long as we're not going near the speed of light. We're going to equate inertia with mass. They're not technically the same thing, but as long as you're not going near the speed of light, sure. The more mass an object has, the more inertia it has. Inertia, or mass, resists a force. You can think of mass as a measure of the stubbornness of an object, the amount of inertia. The more mass an object has, the less willing it is to change its motion state. I was in a car accident once. I was driving on the freeway and I got rear-ended by a semi-truck. It hurt. And it was a really neat car accident because of the physics. I got to pause the YouTube video because I need to stand up. Sorry, those of you watching on YouTube. So here's the short version of Newton's first. If an object is accelerating, there must be an unbalanced force. Good. Or if there's an unbalanced force acting on an object, the object must be accelerating. Remember, though, acceleration can either be a changing speed or a changing direction. So that's how I know if you're going around a corner in a car, even if your speedometer isn't changing, since your direction is changing, you are accelerating. There is an unbalanced force acting on you. Has to be. Has to be. Oh, yeah, I can do a Chris Angel trick. I can make some money off of this, so pause. So force is definitely a vector, since direction makes a difference. How does Newton's first law help explain how seatbelts save lives? Yeah. You can take the mask off now if you, or you don't have to, but. Newton's, if without the seatbelt, in fact, we used to make a joke that before seatbelts were mandatory, if you were sitting in the front passenger seat, you'd be the first one out to inspect the damage. And the joke was you'd be going through the windshield, and as you went over the hood, you'd inspect the damage just to make sure there wasn't any damage, right? That was our morbid joke. Yeah. So, person would keep going in straight line. It's such a simple concept. We have mandatory seatbelt laws. Many places in the U.S. don't because they value their freedom over science. Dumb. Okay. What do you yell when you want the front seat? What do you yell out? Why is it shotgun? Well, there's two origin stories to that. From the old stagecoach days, the person who sat on the right side of the driver was carrying the shotgun to prevent bandits from robbing them, and that's sort of where it came. But also in the 50s and 60s, before seatbelt rules were mandatory, it was our joke. We would say, I got shotgun, I'll be the first one out to inspect the damage. You were going to go through the windshield. Okay? Why wouldn't you want a seatbelt on a motorcycle then? There also, because the motorcycle and you have roughly the same amount of inertia, you're going to tumble together in the wreckage, and you're going to be, that's not what we want. We would prefer you to be separated from the wreckage in a motorcycle car accident. But in a car surrounded by a chassis of steel, you're much safer in the vehicle. We'll do a couple more and then we'll be done. We'll pause. Next page. This is where Newton's first law, especially if you know that an object is not accelerating, can come in very handy. So Manuel weighs 1,000 newtons. Gravity's pulling down on him with 1,000 newtons. And he stands in the middle of a board that weighs 200 newtons. What's the total force down, grand total? Deegan. 1,200. Is this board sinking into the ground like quicksand? Say no. Is it flying to you like Superman? Say no. So is it accelerating? Then the net force has to be 0. How hard must each of those scales be pushing up if the total force is 1,200 down? It's got to be 600 apiece. Has to be. That's Newton's first. That's the power of Newton's first. Now Manuel is no longer dead center. He's moved off to the left. So one scale is having to push up with more than 600. It's pushing up with 850 newtons. How much must the other scale be pushing up with if the whole system is not accelerating? 350. Has to be. Because we're not accelerating down, so the net force up has to be 1,200. Yeah. And if forces are balanced, no acceleration. You can use this also to look at how bridge design is made. The total force down on this bridge is 12 tons from the truck, 20 tons from the bridge, 32 tons. If this bridge support is pushing up with 13 tons, how much must this bridge support be pushing up with? Got to be 19 tons. Has to be. Newton's first. In terms of Newton's first law, the law of inertia, how does a car headrest help guard against whiplash if you're in a rear-end collision? And think the subway sleeper video that I showed you. Yeah, Aiden. Your head it has a fair bit of mass. It would stay, quote, at rest, but your body would get thrown forward. Now, you would think your head got flipped back. It did not. Your body gets thrown forward. We'd like your head to stay with your body. And that's also, once you buy your first car, first thing you want to do, adjust the headrest. It's such a minimal, easy thing to do, but you don't want whiplash. You don't want a neck injury that haunts you for the rest of your life. Okay? So yeah, head would remain at rest. So the headrest, even though we call it a headrest, we should call it a head force. It actually is applying a force on your head to keep your head with your body.